is we're going to be doing what are called optimization problems. So you are looking for these in most cases to find a maximum or minimum. And obviously this is what we've been doing, finding relative maximum minimums or absolute maximum minimums here. But we'll be starting just from a situation. We won't have an equation to begin with. We'll have to come up with the equation for it. So a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So open box means that it does not have a top here. And we want to have a square base. I know surface area is going to be 108 square inches, and I want maximum volume. So if you are packaging something in particular, you may have certain parameters that you are limited by. We've decided what those are here for you, but this could actually possibly happen. So square base and 108 square inch surface area. So if we draw our box here with a square base. So in our square base, I'm going to call, let me see if I can draw that a little better. Just drawing all these crazy lines. It's working against me here. And we would know both of these sides would have the same length if we've got a square base. So we'd have two sides here. I'm going to call them both x. I don't know the height for this one. So you're going to have, for pretty much all of these problems, you're going to have two equations. You're going to have the equation that you actually need to maximize, and then a second piece of information that you can use that you're going to have to plug into that equation. So what are we trying to find the maximum of? Volume, maximum volume. So volume of this box here, for a box, volume is just length times width times height, so that would be x times h, or it would be better to write that as x squared times h. Okay. We need to find the maximum of that equation, but right now that equation is into, well, 3 variables, right? And we need to get it down to at least 2 variables or we're not going to be able to deal with the answer that we're going to get. So we have another piece of information. We know the surface area has to be 108. So for whatever reason, we can only have a surface area of 108, whatever the perhaps the material that we're working with, that's how much we want to use per package, right? So how do I find the surface area of this box here? Remember, it does not have a top. It only has a bottom. What? That would only be true if the height was also x. So you're just like adding the area of all the sides together, right? So what would the area of one of these, like this front side, be? X times h. What about the side over here? Also x times h. The back is x times h. The left side here is x times h, right? So all 4 of the sides are going to be x times h. So we're going to have 4 x times h. And then what's the area of the bottom? X squared. Okay, so So, I also know the surface area here is 108. So it's 108 equals 4xh plus x squared. So more or less what you're going to be doing here is some high-level substitution, right? I need to show this to my Math 1 kids. We're doing substitution right now, just so they can see where it goes one day. So high-level substitution. So it really doesn't matter whether I substitute into this equation for the x or the h. I want to have all the same variable. So, and I want to take this equation and plug it into volume, because volume is what I'm looking for the maximum of. So, which variable could we solve for most easily over here? H, because there's only one of them, right? So, x would be very difficult to solve for. You'd have to do like some crazy complete and square sort of stuff to solve for h there. For x, h is much easier to solve for. So you would just do 108 minus x squared would equal 4xh. And then divide by 4x. And you got a couple ways to deal with this. I would do love connection here. You can leave it a fraction if you want. But I would do love connection. And, let's see, that's going to be, what, 27? I would make this 27x to the negative 1 minus 1/4 x. Now, you could leave it a fraction. If you leave it a fraction, it just may make it a little more difficult to deal with when you have to do a derivative. So since h is equal to all of this stuff right here, I can plug h into this equation. So that will give me v equals x squared times 27x to the negative 1 minus 1/4 x. Okay, I'm going to stop for a second. What questions do you guys have? Yes? Not necessarily, no. Only the base is square. So you could have like a square on the bottom and just be like a really short top or really tall. Yeah. Okay. All right. Other questions? Okay, so this is the really hard part about this, like the reason through and coming up with the equation. Once you have your volume equation, because we want to find maximum volume, in terms of one variable, what you need to do is just what we've been doing in class. You need to take the derivative, find your critical points, decide if you have maximum or minimum, right? It'll be easier to do your derivative here if you distribute that x squared. Because that'll give you 27x minus 1/4 x to the third. That way you just have to do power rule. You don't have to do anything fancy there. So if we take the derivative of this dv dx, we'll get 27 minus 3/4 x squared. We okay here? Yes. V prime's fine. Yeah, you can call it V prime. And so when we're finding maximums and minimums, we're going to take our derivative, we're going to set it equal to 0 to find critical points. So in this case, if I move this stuff over, I've got 27 equals positive 3/4 x squared. How do I get rid of that 3/4? Multiply by 4/3. Or divide by 3/4, but that's just going to multiply by 4/3. So, you know, some of these you'll be asked to do without a calculator. So this would reduce here. You get 36 equals x squared. And then we will square root both sides. So we get plus or minus 6 for our x. But for this particular equation, does it make any sense to consider that negative 6? It does not, because the smallest x would be 0, right? You can't, I mean, technically it can't even be 0, but it could be close to 0. So I'm going to ignore the negatives in this situation, and in a lot of these problems you will ignore negatives because it doesn't make sense to have a negative value in this situation. So if I think about what I'm doing here, because 6 is my only critical point, it seems likely that this would probably be the maximum, but you do want to check. So if you plug in a number like 2, 27 minus 3/4 times 2 squared would be 27 minus 3. You'd get a positive right here. But if you plug in a number bigger than 6, so if we plug in like 10, 27 minus 3/4 times 10 squared, it's 3/4 of 100 is bigger than 27, so we get a negative right there. Because in our situation, we're talking about the side of a box, the length of the side of a box, and so you can't have a negative length. So a lot of these, like application problems, the negatives don't really apply to the situation. Now, as far as that equation goes, the negative 6 is a critical point and could be a maximum or minimum, but for the situation, it just doesn't make sense. And that's why I put the 0 here. 0 is not really a critical point, but your length of your side can't be below 0. Okay? All right, so we do see here that this is a maximum. So x would equal 6, but it asks for dimensions that would produce the maximum volume. So I also need to know height. So what would I do to find that height? Plug the 6 back in to what? Surface area, because that's the only one that has, like, volume has too many variables in it. This, if I plug in 6 here, it's going to give me the volume. It's not going to give me height. So I need to go back over here to this. Actually, I could do this one, although I don't know that that's easier. It might be. Well, whatever. So we got 108 equals 4 times 6h plus 6 squared. So 108 equals 24h plus 36. We would subtract 36. And that will give us 72 equals 24h divided by 24. And 3 is our height. So 6 by 6 by 3, what are we measuring this in? Inches. So 6 inches by 6 inches by 3 inches. That would give you your maximum volume. A problem like this is usually not going to require justification. So if it were, this would be like a part of it if you saw it. You would just need to state 6 inches by 6 inches by 3 inches. Would be fine. Here, these are more likely to be seen on multiple choice. They don't usually put these on free response. which seems a little odd because they're such long problems. All right, questions? So it's kind of cool. That'll give you the maximum volume. If it asks you for the maximum volume, you just plug in, or really, I mean, if you want volume, just 6 times 6 times 3 would be your volume there. Okay. Questions? I would say sometimes packaging places probably aren't even going for maximum volume. They're going for like maximum surface area because they want the package to look big, even though it may not have much in it. Okay, so this is just like a purely mathematical problem here. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So I'm going to graph this on Desmos just so we can get a picture of what it looks like. So we got f of x equals 4 minus x squared, and then we got the point, point 0, 2. So let me just paste this over here so we can, nope, that's not what I meant to do. Alright. Alright, so we could do this without Desmos, but we know this is a parabola, it's upside down, its y-intercept is at 4, and then the point 0, 2 is right here. So, we want to know which points on the graph are closest to 0, 2. So, if you think about it here, I know the points are not going to be like down here, right? That's too far away. But the question is, are they the points that are like right here? Or with more of a diagonal approach, I think that looks a little bit closer than these lines right here. But like, where is that? You can't just like clearly see, oh yeah, that's the closest point here. So, we need to come up with some sort of equation that we can use that will give us the exact answer for this. Okay? So, in this case, what are we trying to find a max, its closest point, so it's a minimum, right? What are we trying to minimize? Distance. Distance from 0, 2 to the parabola. That's what we're trying to find a minimum of, right? Anybody remember distance formula? The square root. This is long ago. Math 1. You may have pulled it back out in some of the other math classes, but definitely Math 1. Okay, distance formula is x1 minus x2 squared plus y1 minus y2 squared. It's a form of Pythagorean theorem. When you subtract your x's, it finds like one leg of the triangle. When you subtract your y's, it finds the other leg. And then it's a squared plus b squared equals c squared sort of deal. There. So this is a formula that we should probably know. So I know one of these points is 0, 2. I do not know the other point, right? I've got mystery point over here. I'm just going to call it xy. So, but I could plug this into my distance formula. So I've got x minus 0 squared plus y minus 2 squared. Now, that formula is in two variables. I need it to be just one variable so I can deal with it. What can we do? The other equation that we need to use to plug into this one is already there. You could do that, but it will be even easier if we just plug this in for the y. Because it doesn't necessarily have to be one or the other variables. It doesn't matter which one. So you could definitely do it that way, and then you'll find the y value that gives you the maximum. But it'll be a little bit easier because you'll have square root and stuff to deal with if you do it the other way. And we can do that because this point xy is on the graph, and so if it is on the graph, the y has to equal 4 minus x squared. So this is just going to be x squared, and then we got 4 minus x squared minus 2 squared. So that is going to be x squared plus 2 minus x squared squared. All right, so this is what we need. We need to find the minimum of this. However, I don't even really want to think about taking the derivative of that. Even if I simplify what's on the inside a little bit, I still got that square root, which means I'm going to have to make it to the 1/2 power, and then I get like 1/2 that to the negative 1/2. I get roots in the bottom times the derivative of the inside. The derivative of that is not simple, right? However, if we have a maximum of the inside stuff, it's still going to be a maximum if we take the square root of it, right? It's going to be less, but it's going to be still a maximum point. So to deal with this, to make this easier, the maximum of just the inside also has to be the maximum whenever you're taking the square root of the inside, right? It's not going to be the same number, but it's still going, the x-coordinate is still going to be the same. So, the way we can deal with this is we can say let f of x, just make sure this is not something that's already in the problem. They didn't call this f of x, so like if they call this f of x, I need to use a different letter. I'm going to say let f of x equal x squared plus 2 minus x squared squared. If f of x has a maximum at an x value, D also has a maximum. So if we can just find the maximum of f, then we can say that's also the maximum value for D. And that's going to make it a lot easier to do this problem, because f of x, I would probably go ahead and double square that. So that would be plus 4 minus 4x squared plus x to the 4th. If you double square your 2 minus x squared. So f of x would just equal x to the 4th minus 3x squared plus 4. So this is a simple derivative now. It's just going to be 4x cubed minus 6x. We want to see where that equals 0. So you can factor that 2x times 2x squared minus 3. So 2x would equal 0, 2x squared minus 3 would equal 0. So x equals 0, and 2x squared equals 3. Divide by 2, x squared equals 3 halves. Square root both sides, so x equals plus or minus the square root of 3 halves. Does it make sense to have a positive and a negative here? It could, because we're talking about the x coordinates of our points. And if you look at your graph, you're probably going, whatever your x coordinate is on the positive side, it's just going to be mirrored on the other side because of your symmetry of this graph. So you do want to keep both of those there. Okay, let me stop for a second and see if anybody has any questions. Yes?
Why is the derivative of f of x equal to square root of x?
It doesn't equal the derivative. Like, they're not going to have the same value. But if we have a maximum of f, that x coordinate is also going to give us the maximum of y, or of d. Because if we have a maximum at square root of 3 over 2, that means that's the biggest this number on the inside is ever going to be, right? And so the square root of that is also the biggest it's ever going to be. So it's not necessarily that like the y values are going to be the same, but the x values will be the same where those occur. Does that make sense? And you could do this using this as your, like taking the derivative of d. It's just harder because here I had a really easy derivative to take. This is not an easy derivative, so it just makes it a longer problem. It could still work for relative minimums because relative minimums might still be positive values. For this particular, you know that the absolute, you know that the distance always is going to need to be positive there. So, which actually distance formula ends up always being positive under the root anyway because you're squaring both pieces and then you're adding them together. So x values could be negative here. You won't get a negative y for those. I ignored it. So what we're doing here is we are kind of reasoning through it. So I could do this whole thing using d as my function and taking the derivative of that, including the square root. Because that would work. But that square root makes that derivative difficult, right? So what we're saying here is that if this stuff on the inside that I have in that green box, which I have called f, if it has its maximum value, like if it's the highest at square root of 3 over 2, then the square root of that also has to be the highest it's ever going to be. So we can say, because there's nothing else added to this, since it's all under the square root, if f has a maximum, then d is also going to have a maximum. So we are ignoring it. You cannot do that on every problem, but if you ever have a problem like this where everything's under the square root, you can, and it makes it easier to do. Okay? All right, so let's do a sign line. We've got negative root 3 over 2, 0, and positive root 3 over 2. I'm going to make the chart. You don't have to, but we need to think about these signs. So here we just have negative, negative, positive, positive. Here we're going to get positives on the outside, but if we plug in a number between square root of 3 over 2, negative square root of 3 over 2, and positive square root of 3 over 2, we'll get negatives in the middle. So we get negative, positive, negative, positive. There. And we are minimizing because we want to know closest, that's shortest distance. So we would have a minimum here, relative minimum, and a minimum here. All right, how do we know those are minimums from that sign chart? We have our derivative going from negative to positive. So the x coordinates are square root of 3 over 2 and negative square root of 3 over 2. Those are our minimums. So if it's a minimum of f, it's also going to be a minimum of d. And we need to know the point, so we need y coordinates also. Easiest thing to do is plug those into 4 minus x squared. So if x equals negative square root of 3 over 2, y would equal 4 minus negative square root of 3 over 2 squared. That square will get rid of that negative, and we'll just have 3 over 2. And that is going to be 5 halves. Right? And for x equals positive square root of 3 over 2, your y is going to be 4 minus square root of 3 over 2 squared, which is going to give you the same thing, 5 halves. So your points are going to be at negative square root of 3 over 2, 5 halves, and positive square root of 3 over 2, 5 halves. Those are your closest points. So if I flip over to Desmos to graph those, we'll see where they're at exactly. Alright, so you got these 2 points here. So it's kind of slanty, but not like straight up to that nice even point. So it'd be difficult to figure that out, you know, just by looking. We get like in the ballpark, we were looking somewhere around here. But those are the absolute closest to that point. So if you find a problem like this that is asking you the point that's closest to a graph, you want to use distance formula for that. Okay, questions there? Oh, I should have said minimum. That was wrong. I mean, it would also be true for maximums. But we are looking for minimum, so I should have said minimum there. Okay, questions? Okay. Let me look at which ones are homework tonight so I can know which ones I need to do tonight. Because we're going to work on these tomorrow as well. So, let me see here. You would think I would go in order, but I might not have. Let's see, today, 16, 17. Alright, we got one page. And okay, we need to do this next one, and then we're going to stop for these today, and you'll have 4 of them for homework, and then we'll do the other 3 tomorrow, and we'll do some more practice with those tomorrow. All right, so rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should be the dimensions of the page so that the least amount of paper is used? So, let's draw what we've got going on here. We have a sheet of paper, and we have margins that are 1.5 at the top and bottom and 1 on the side. So, let's try to draw it where it looks about right. Something like this. All right, so we know that our length here is 1. Our length here is 1.5. And so we know we want to contain 24 square inches of print. That is the inside part of this. But we want to minimize the amount of paper, so that would be the whole sheet of paper. So we really have a couple options here on how we want to do this. We could let the outside of the big sheet of paper be X and the inside and the outside of this be Y, right? Or we could let the inside part be X and Y. Almost. You're a little off. So if I let this out, I'm going to go with what Connor's saying. This is X. And this is Y. And so if this is X and this is Y, you got 1 on either side. So this would be X minus 2. And this side right here would be Y minus 3. The margins are 1.5. So you got 1.5 inches up here and another 1.5 inches down here that are being subtracted. And same thing here, you got 1 here and 1 here that you're subtracting. You could also do this where the inside is XY and the outside is X plus 2 and Y plus 3. So either is fine. Is one going to be easier than the other though? Might. I think it's going to be easier with XY on the inside. I mean, you're going to run into the same problems either way, but here's the what's difficult though is that you got 24 equals X minus 2, Y minus 3. You can solve it. I guess it's going to run the same thing. Solving that for X or for Y is not the easiest in the world. The area of the big sheet of paper would just be XY if we do this. So I'm going to stick with what Connor's telling me to do. Although I'm inclined to do XY on the inside. But we've already began. So, alright, how am I going to solve this? Doesn't matter if I solve for X or Y. It's not, and neither one of them is necessarily going to be easier than the other. Let's say that we solve this for Y. If we're going to solve this equation for Y, what would you guys do first? you're going to divide x minus 2. You're not going to distribute, because if you distribute, you're going to have an xy together. That's going to be difficult to separate. And then, once you've divided by the x minus 2, what should you do? Add the 3. So we're going to get 24 over x minus 2 plus 3 equals y. Okay, here. Alright. Now, the reason we need to do that is because we need to plug it into the area formula, which is the formula that we're actually minimizing, right? So we're taking this stuff and we're plugging it in for the y. So I have that my area is going to equal x times 24 over x minus 2 plus 3. And I would go ahead and distribute that there. So I've got a equals 24x over x minus 2 plus 3x. Are we okay here? I'm trying to decide whether I'd rather get common denominators first or just go ahead and take the derivative here. I'm inclined to just go ahead and take the derivative because 3x is easy to take the derivative of. So I think I'm going to do that. So if I'm taking my derivative, a prime would be, you got to use quotient rule here. X minus 2 times 24 minus 24x times 1 over x minus 2 squared, and we'll just have a plus 3 over here. So if we simplify that, we've got 24x minus 48 minus 24x over x minus 2 squared plus 3. These cancel. And we got negative 48 over x minus 2 squared plus 3. And you want to know where this equals 0 or undefined. You could get common denominators, but if you do get common denominators, x minus 2 squared is going to be your denominator, right? So you could just go say undefined is going to be if x minus 2 squared equals 0. And so that's going to be x minus 2 equals 0 and x equals 2. Alright, so undefined is going to happen at 2. Then you could take negative 48 over x minus 2 squared plus 3 and set that equal to 0. And you can move the 3 over. Negative 3. Multiply both sides by square root of x. Put this over 1, cross multiply, however you want to think about it. Divide by negative 3. X minus 2 squared is going to be 16. Square root both sides. So x minus 2 will equal plus or minus 4. So x will equal plus or minus 4 plus 2. And so that gives you x equals 4 plus 2, which is 6, or x equals negative 4 plus 2, which is negative 2. But would a side length of negative 2 make sense for the side length of a piece of paper? Probably not. So we got 2 and 6. Whew. I might should have got common denominators. 2, 6. You got to plug back into the derivative here, which I can't make a chart for because I didn't get common denominators. So if I plug in 1, I got negative 48 over negative 1 squared plus 3. That's going to give me a negative there. Between 2 and 6, like for 3, if I do negative 48 over 3 minus 2 squared plus 3. Hold on, did I do something wrong? 3, 2, I don't think so. So that's still negative. And then if I put something bigger, like 10, I get negative 48 over 64 plus 3. That's going to be positive. So, relative minimum right here. So, we got 6 inches for our x. And then for our y, we could plug 6 back into our y equation, which was here. So y equals 24 over 6 minus 2 plus 3. So that is 24 over 4 plus 3, which is 6 plus 3, which is 9. So 6 inches by 9 inches would use the least amount of paper. There. Alright, so your assignment for tonight is going to be page 262, 16, 17, 20, and 33. 33, I think, is actually a couple pages over. So, I know that these can be a little bit difficult to set up, but try something on every problem. 20 and 33.